Hello, this is our fall CBE 205 final. We did this in the form of a storybook called Frank Learns Metabolic Flux Analysis by Cassandra, Lauren, and Ashley. On his way home from a long trip, Frank the Penguin bumps into his old friend Roger, who has a background in metabolic engineering.
Roger, hello, it's me, Frank.
Frank calls eagerly from across the train station.
Well, hello, Frank. Fancy meeting you here.
Roger happily remarked. Frank excitedly says,
I just got a job at Richardson Engineering, and I'm so excited to start. The only problem is I'll be working on a project using metabolic flux analysis, and I don't really know what that is.
Roger replied.
Well, lucky for you, since I last saw you, I became the best metabolic engineers in my company.
A train then arrives.
I'm so glad we were on the same train and that you know lots about metabolic flux analysis. Could you help me understand it?
Inquired Frank, ready to investigate this topic.
Of course I can help. Metabolic flux analysis is my favorite. Get ready for a fun adventure,
replied Roger excitedly, and so their metabolic engineering adventure begins. Roger, excited to share his knowledge, says,
Okay, first we have to understand what the metabolites and rate reactions are. This is because these are the main components needed to model cellular metabolic processes. Let's take a look. A metabolite is something like a molecule used or produced in a reaction. The reaction rate shows how fast these metabolites are used up. Based on how fast these metabolites are produced and consumed, we can model and predict things about the metabolic process.
That makes a lot of sense so far. Now that I understand the basics, let's keep going,
explained Frank.
Well, let's see how I should put this. Oh, I know. I can put this in the context of trains to make it a little bit easier to understand. Now, in our context of trains, we can think of the speed of each train as the reaction rate and the contents of their cargo as the metabolites. The trains travel all around at different speeds and over different terrain, but at different depots they exchange cargo. At their final destination, they have a final load of cargo, like the final product of the metabolic process.
Frank, eager to learn more, quickly asks,
So how do I use this to get more information on my metabolic process?
Well, you can draw a simplified picture of all the routes of the trains, which help you stay organized. Let's take a look at how to do that.
Roger replied.
So we could draw something like this. You can see V1 through 10 labels are reaction rates and S1 through 6 are the metabolites. You can easily see metabolites being converted into other metabolites and at what rates,
states Roger.
We use the matrix to solve for the rates in the metabolic process. We need to input our data into a matrix. First, I'm going to show you how to write simple mass balances for each reaction that will make this very simple,
replied Roger.
The simplified mass balance looks like this. In other words, net rate of formation is how the concentration changes over time. So we can think of any reaction rate that removes a metabolite from the process as negative formation and any reaction rate that adds to the concentration as positive formation, which tells us which rates need to be positive and negative in our matrix. Using the first metabolite in our example, S1, we get the positive V1, positive V8, negative V5, and negative V9.
Explains Roger.
The most important thing about this mass balance is that we can apply a pseudo-steady state assumption based on the idea that metabolite levels return quickly to normal after perturbations. This means that the change in metabolite over time is 0 for the intracellular mass balances. We will be putting in the positive and negative coefficients from each of our previously written equations. This will look like this with the pseudo-steady state assumption. First, we need to do some experiments to calculate a few reaction rates. We need to find enough rates so that our equations plus our measured values equal unknowns. Using these, we can make new matrices that we can use to calculate anything we want to know about the metabolic process. We need to create these 4 submatrices: BM, GMT, BC, and BCT. Those matrices are going to look like this. Now we can finally use matrix multiplication to calculate our values. This is the equation we will be using. I find it easiest to plug my matrices into MATLAB to solve, and then I get a nice neat vector of my unsolved reaction rates.
Frank says,
Wow, I think this sounds doable. Next, I'll try some practice problems before I start my job.
Great, I'm always glad to help. And yes, lots of practice and you'll be a whiz at metabolic flux analysis.
Roger replied happily.
And with this knowledge, you can do incredible things like produce chemicals, medicine, and fuels from living cells. I'm excited to hear all about the incredible things you will do at your job. Best of luck,
says Roger.
Thank you. I look forward to talking about metabolic engineering again soon.
Frank replies. The end.